Hello AP Chemistry and welcome to ionic bonding. So we talked previously that ionic bonding is the exchange of electrons, right? So we know that electrons are actually changing hands, okay? So we are doing the exchange of electrons. So for example, if we were looking at Lewis symbols, right, we would have a sodium plus a chlorine, and that's going to give us an Na. So what's going to happen here in terms of electrons, right, is this is going to go over here, which means that sodium now has a +1 charge. Chlorine has an extra electron, meaning chlorine now has a -1 charge, right? Now here we have two charged particles, which means we have an electrostatic interaction, okay? Or an electrostatic attraction between my sodium and my chloride, right? And so when we're talking about this, right, Coulomb's law would be appropriate to talk about the relative strengths of ionic attractions, okay? So here we have the essence of an ionic bond. Do be mindful, this is a redox process, right, in that there is a give and a take of electrons. Okay, next up, how could we identify each element without colors? And this also sort of demonstrates why ionic compounds are brittle, which is why, for example, when you take salt, right, it's relatively easy to crush salt and turn it into smaller pieces, right? Because, right, they have all these electrostatic attractions, right? We have pluses stuck to minuses. If we apply a shear force, right, meaning an angled force, and one of these layers becomes off-centered relative to its neighboring layer, instead of having plus and minus attractions, we have plus repulsions, or minus repulsions, right? Which is why they are easy to apply shear force to and get them to break apart, right? Meaning they're brittle. Now, back to the question up top, right? How could we identify each element without color? So here they have a nice color coding for us, right? But even if you weren't given that, you should be able to tell me that these are my sodiums and these are my chlorides. Why? That goes back to our periodic table and our trends, right? So if you look at sodium and chlorine and we look at a periodic table really quickly, right, we see that sodium and chlorine are actually in the same period. So then you might think to yourself, why is this peculiar? Right, because hypothetically, right, if we were comparing a neutral sodium to a neutral chlorine, chlorine would be smaller. But are we talking about neutral species? No, right here we're talking about a sodium ion, specifically a cation, which means, right, we've lost its valence shell, which means now we're talking about the core of a sodium, which means that now this sodium looks a lot like neon, right? Wherein chlorine looks a lot like argon, which in this case means, right, that my chlorine ion is going to be bigger than my sodium ion, right? So we should be able to deduce that on our own, okay? Now, going back to full screen to be all fancy. So anyway, in terms of analyzing the energetics of the formation of an ionic compound, right, here we have what's known as the Born-Haber cycle, right, which is just kind of a giant diagram of Hess's law as it applies to the formation of an ionic compound, okay? So, looking at our energies, right, here we have our solid sodium and our 1/2 chlorine gas, right, and this is because we're going to use heat of formation as one of our constants, not constants, but like points of reference, okay? So we have our solid sodium, which we would then turn gaseous because all of our other information is about gaseous species, right? So we would turn sodium gaseous, which means input of energy, yes? Okay. Here we have our chlorine, which we're going to split apart, another input of energy because we are breaking bonds, okay? Here we go from sodium to sodium ion. This is labeled I, right? It could just as well be labeled IE for ionization energy, another input of energy, okay? So we have to input all of this energy before we can start getting energy out. All formation of ionic compound reactions are exothermic, meaning energy comes out, okay? So if we come over here, right, this is what energy is this associated with? Right, this is the electron affinity of chlorine, right? In that we are adding an electron to gaseous chlorine. Now, if we look here, right, this is still not an output of energy, right? So there's still got to be something else that gets us the rest of the way down. And that is known as lattice energy, okay? Where the definition of lattice energy, right, is the amount of energy necessary to take a solid ionic compound and break it apart into its gaseous separated ions, okay? Lattice energy by definition is the amount of energy needed or required or that must be put into a solid ionic compound to break it apart into separated gaseous ions, which means that it's a reflection of the strength of an ionic interaction, right? The stronger, the more attracted those ions are to each other, the greater the lattice energy, okay? The stronger the attraction, the greater the lattice energy, right? Which from the flip side means if I take those gaseous ions and I turn them into a solid, right, that's how much energy I release. Yes? All right, fantastic. So some trends in lattice energy. So going back to Coulomb's law, right, we have charges and then we have distance. Charge is always going to be our more important thing when we're talking about ionic compounds, because charges are always going to scale by whole numbers, okay? Charges scale by whole numbers, right? My charge is either going to be 1 or it's going to be 2 or it's going to be 3, which means that my force literally gets multiplied by 2 or by 3 or more, okay? Whereas my diameter is not going to change quite as much, right? Going back to that diagram of atomic radii, even going from the top of the table to the bottom, okay, fine. If we start at period 2 to the bottom, right, we might be talking about doubling my radius if we compare something from the top and the bottom, okay? So anyway, let's talk and compare some of these. So if we compare these three, right, lithium fluoride, lithium chloride, lithium iodide. So what do we notice about this set? Right, they all start with lithium, and then we start with fluorine, then we get to a slightly bigger anion, and a slightly bigger anion, right? And they all have the same charges, yes? +1, -1, +1, -1, +1, -1, okay? Which means that charge is not what we're discussing for this set. We are going to be discussing the diameter. Now, lithium is obviously constant. What do we know about the size of fluorine relative to the size of chlorine relative to the size of iodine? Right. We know that iodine is bigger than chlorine is bigger than fluorine, which means that this one has the biggest diameter, the lowest force of attraction. Yes, this one has the smallest diameter, greatest force of attraction. Yes? Okay, now let's compare some different ones, right? So here, if we have our lithium chloride, for example, let's try. If we have lithium chloride, and we want to compare that to, let's do something comparable. Magnesium chloride. Okay. If we look at those two, and we look at that energy difference, what do we notice? Right, we notice that this one is much bigger. If we even add sodium chloride to the mix, right, we see that, again, much, much bigger still, right? Why is magnesium chloride's lattice energy so much greater than lithium chloride or sodium chloride? Right, double the charge, right? This has a charge of +2, which means that we've literally doubled the force of attraction, right? So Q going to be the biggest factor, right? If we look over here, these are all significantly greater than those or any of these. What's the difference here? Right. Both of them are doubly charged, right? Which is why these get much, much bigger than these and much, much, much bigger than these, right? And by the time we get to 3 and 3, right, scandium is +3, this is -3, right? It goes up even more, okay? So the greater our charges, the greater our lattice energy, the stronger the force of attraction, right? The smaller the distance, the stronger my force of attraction and the greater my lattice energy. Okay. Next up, this is just another figure that sort of corroborates that. Oh, and that's the end. I didn't pay attention to my yellow dot. All right, thanks for listening. Be good. I'll see you soon. Bye.